Welcome everyone. We have discussed in last two class about high level synthesis. So, what we have seen that this high level synthesis consists of scheduling, allocation binding and data path and controller generation, and we have seen in the last class how to automate those steps, and we have seen also that those steps mostly NP completes, and we primarily heuristic based algorithm are widely used in high level synthesis industry. So, that part we understand that background algorithm steps and all. So, now from the designer perspective, when you try to write some C code or say abstract code in MATLAB or say Simulink or say in C++, and you try to use some industrial high level synthesis tool to design the RTL, what are the things you should be aware of? What are the things you should keep in your mind when you are writing your C code? So, that is something is the discussion topic today. So, today we are going to discuss coding style. So, this coding style is applicable to is basically irrespective of the language specific, but we are trying to follow C because C is the most commonly used interface for most of the industrial synthesis high level synthesis tool. So, but this is something you can this kind of logic that data types or say loops and that are applicable to other language also. So, this style coding style that we are going to talk about is kind of mostly it is language independent and is applicable for any kind of language that you are going to use. So, so the outline of today's presentation is this coding style, and primarily we are going to discuss about the impact of different kind of part like function, data types, data path width, then loops, array, I mean they how to use them and how they are impacting the generated hardware. So, what are the things you should be aware of or be sincere of or be careful about when you are writing your C code, so that the kind of hardware you are going to generate will be optimized one or the efficient one in terms of power or in terms of latency, right. So, that is something we are going to discuss. So, first we are going to discuss the data types. So, in C we try mostly use data types like integer, long int or say float, those kind of data types, right. So, and when you are writing C code, we are not bothered about exactly what kind of input we are going to give, right. So, I mean we define something integer, but maybe our values are maybe only, so integer mostly is basically 32 bits, but most of the time maybe your case that your data may not go more than 10 bits or 12 bits. But we do not care those things when you are writing C code, because it does not matter. So, even if it is a 10 bits data, but if you are using 32 bits integer, it is fine, there is no problem. But if you just think about you are going to map it to the hardware. So, when you are going to map it to hardware, that instead of 10 bits, if you are writing a generating 30 bits or say 32 is your 32 bits hardware, your size of your design goes 3 times bigger than the design that has only 10 bits data path, right. So, if you just think about you have say A equal to B plus C, right. So, if you just design this in and you say this is all 10 bits, right. So, these are all 10 bits. So, this will result in one full adder which is of the inputs are of 10 bits and the output is of 11 bits, right. But if you just think about, if you write in C, this A is basically you just define this A int A, B and C, right. So, effectively when if I assume that my ABC all integer are 32 bits, then the full adder that you are going to generate effectively is of 32 bits, right. So, this is all 32 bits, right. So, the problem is here this is a full adder. So, if you just write this A equal to B plus C, so effectively it will generate a full adder of size 32 bits, right. So, the problem is here is that if your data types or the data value you are going to use is very less, not integer, you should use a very customized integer type, which is a 10 bits or 12 bits. And you might ask the question, how do I represent 10 bits or 12 bits in C, right. but mostly in C we do not have option, but we are going to use this for any synthesis tool that has the option to customize your data width. So, for example, if you go for this Xilinx Vivato, they have this customized data type. You can declare int 12 or say int 24. So, instead of 32 bits integer, you can use 12 bits or say 24 bits integer. So, that is one aspect you should always be careful, because when you are writing C code, we never give concentration or give weightage on this aspect, but very simple thing, just if using without knowing this randomly integer, long integer, your data path will be higher, which is not required for your design. Most of the time those are basically useless. So, the data types are a very key factor for your design. So, whatever I just mentioned here, the data types are used variable determines the area and performance. So, the area and performance will be used by the data types. So, that has to be taken care carefully. So, this is something we always missed, but when you are writing some C code or say C++ code trying to map it to RTL through some high level synthesis. So, you should be always careful about the exact data path size. You should know that your application area, whatever the input width, and you specifically set your data path width according to your according to a requirement, and that will actually reduce the area of your design. So, this is a very simple thing, but that has to be taken care. Okay. So, data type is one issue that we should taken care of. The next thing we are going to discuss about function. So, we write a lot of functions. When you are writing code, we try to make the code modular. So, we use a lot of functions. So, we should know how the function will be get mapped into the hardware. So, that we should understand. So, when you write a function, that function body will become a module in the RTL, right. So, that become a module, and whenever there is a call to that function, that particular module get instantiated. So, why we write function, because we try to reuse it in multiple places. So, in hardware also, whenever you declare a function, it is basically defined as a separate module in the hardware, and wherever you call that function, we instantiate that module once, right. And now, depends on the way that a synthesis tool works, maybe this two call is not data dependent. So, you can actually utilize the same module for both the call. So, it depends on the synthesis tool, or most likely if there is no dependency, they are running in parallel, that part has to be there. So, basically we have only one instance of the module in the hardware, and that is going to be used for both the calls, right. So, that is something. Suppose this is your main, right, and you have say function, you call this function for say value a b here, and after some time again you call the same function for say c d. So, there are a lot of code in between. So, it most likely that you have the one module will be instantiated for the function fn, and this particular instance will be called, and it has two input. The argument will become the inputs, and the return value become the output of that function, and that return types. So, this is the module will be created in hardware, and once you call this function first time with a b. So, a b will be passed to the parameter, and then it will calculate this, and it will return the value that will be stored in variable d. Again, when you call this function c d, and I am assuming here there is no data dependency. So, we are going to call the same function here with the value c and d. It will compute whatever is going to compute here, and then return the value that will store in e. But if there are two calls, there is a data dependency, or it cannot be parallelized, right, then probably it will create two instances of the same module. So, that is something in hardware, but what the important point said is that you should understand how the function is get implemented and how it is going to use. So, most of the time the synthesis tool try to maximize the resource usage of those modules, and wherever is possible. So, that is something is going to happen for functions, right. So, one more point has to be taken carefully when you are writing a function. Again, the data types, right. So, how do you decide how the data type data width within the function is determined, right. So, that has to be also understood from the designer's perspective. So, the important point is here is that when you write a function, the data path width is determined by the input width. So, if your data path width is say 10 bits, so and if you have added here, so the output will become 11 bit, because you are doing this. If there is a multiplier in the function body, then output will be 20 bits, right. So, it depends on the 20 bits, it depends on the size of the input, right. So, your input data width is propagated through the behavior to determine the width of the individual module, right. So, if you just to give an example, suppose I have a data path like this. So, suppose I have adder here, there is a multiplier here, and there is another multiplier here, and suppose this is the circuit the function is going to do this, right. So, suppose this is 10, this is 10 and this is say 5 bits. So, what will be the output width, that how do you decide? So, since this is addition is happening, so all are 10 bits, so output will be 11 bits, right. So, this is 11 bits, this is also 11 bits, and then you are doing multiplication, say there is a multiplication up to 11 bits, so this output will be 22 bits, right. And now you are multiplying a 22 bits data with a 5 bits data, so output will be 27 bits, right. So, this is how the data path width is determined. Its so input width will be propagated to the output, and this will determine the intermediate, all the resource intermediate for the width, right. So, that is very important. So, now you have to be very careful about the input size of the function, because whatever the value you are going to give it here, that will be propagated and that will determine the size. As I mentioned in this data type, when you are declaring this data types. So, if you just give arbitrary value like long int, so unnecessary your data path will be bigger and most of the things is unused and your resource usage will be high, which is unnecessary. So, which could have optimized, right. So, here is an example. Suppose you have this, you have written this function where you passing argument a and b, and you are calculating just a star b and you returning that output, right, and you define long int here, and this is integer and this is integer, and output is 24 bits. So, this is a customized version for Xilinx. So, I am using this notation, but for any other tool the declaration type may be different, but they have the option to customize your data path. Okay. So, this is what we are doing. So, now what will happen here, it will generate a module like this, where since your so I am assuming your integer is 16 bit. So, you can assume anything, but I am just assuming it is 16 bit. So, the multiplier will be of 32 bit width, right, because you are multiplying to 16 bit. So, your multiply output will be 32 bits, but here your output is only required is 24 bits. So, basically that multiplier that you are having here 32 bits is waste, right. You have to truncate 8 bits and you have to take the last 20 LSB 24 bits as the output, not the all 32 bits. So, actually you are unnecessarily calculating extra thing which is not required and which is basically getting wasted, right. So, instead of writing this function, if you aware that your since your output record is only 24 bits, so you do not need to give a 16 bit input, right, you should give a 12 bit input, right. So, if you are just rewrite this function, you should rewrite like this way, your integer should be of, instead of int, it should be integer size of 12. So, that it is not generating extra hardware. So, if you just do this, so this is 12 bits, so this will be propagated 24 bits and your output is 24 bits. So, the multiplier will be generated as a 24 multiplier instead of a 32 bit multiplier. So, this is the advantage. So, so this is something we should be always careful. So, just to summarize your function thing, you have to remember two things. First thing is that function is become a module and it gets instantiated whenever it has a call, and try to the high level synthesis try to utilize those functions that module, try to reuse that particular module for multiple calls. So, that is one aspect, and the second input is second important point around function is that data path width within the function is determined by the input data path width. So, you have to always specify the exact data path width which is required for your design, and it is going to be over just for the like general int or long int. If you are going to use, then you are going to generate some extra hardware. So, you can actually optimize that things if you are little bit careful about that. Okay. Okay. So, now I am going to move on to the next topic, which is loop. So, whenever you write any code, the most important two aspect is array and loop, and they have a huge impact on hardware. So, you have to be very careful when you are writing something involving loops and arrays. Okay. So, we will first discuss on loop and then we are going to talk about array, how this array will be synthesized. Okay. So, for loop, if you have a loop body, how it is get implemented, either it is partially get unrolled or it is fully unrolled or pipelined during in hardware. right. So, we will try to discuss that what is that implementation. So, when you write a loop in your program, either it will be unroll, fully unroll, partially unroll or pipeline. Based on the design choice, you can actually give this choice. There is a control when you are synthesizing with some commercial synthesis tool, they have some option to specify this, whether you want to unroll a loop or partially unroll a loop or pipeline that loop, right. So, we will just try to see if what kind of hardware it will be generated if we choose these options, right. So, suppose I am going to take this simple loop where I am just calculating this Ci equal to Ai plus Bi, just adding to array A and Bi from 1 to 10. So, this is the loop is going to iterate 10 times and it will calculate as array size C 1 to 10, right, using the value A and B. Okay. So, now if you just think about the pipeline version of this implementation, the code is written here. So, what is happening here? So, I am assuming this array A and B is used only here and they have only single usage, right. So, I can map those arrays to memory. So, I am infer a memory for array A, I am inferred a memory for array B, I have inferred a memory for array C, right. So, this is inferred and so there is a register for I which has a initial value reset. So, during reset it will be set to 1 and then in each iteration that I goes. So, that is the address to this memory. So, A I will be read and here B I will be read and then I will do just A I plus B I, which is basically C I, and that is getting, this is the data for this memory and the address is I again, right, this is I. So, this is how the whole thing will be generated and we will have this incrementer, this I plus plus, and this data will be written back to I. And also I have the comparator less than equal to, I will just check whether the current I is less than equal to 10 or not. So, so this will work as a write enable to this array, right. So, this data Ci will be updated until you have I is less than equal to 10, right, and this is also the write enable to this register. Okay. So, in abstract level, this is the data path will be generated if you choose to pipeline this array, this loop. Okay. If you pipeline this loop, this is the kind of data path it will be generated. Okay. You can see here that I have only one instance of the loop body. So, this is the loop body, right. So, the loop body I have only one addition operations and in the hardware I am actually have a one instance of that particular loop body, the operator in the loop body, and I am actually pipelining this. So, in first iteration, so first cycle A1 equal to C1 equal to A1 plus B1 will be calculated, right. In the second iteration C2 equal to A2 plus B2 will be calculated, right, and so on. So, I need 10 cycle to complete this operation, right. So, in the pipeline mode I have going to use only one instance of the loop body, whatever the resource required to implement the one iteration of the loop body, that kind of hardware will be used and it will be pipelined so that the number of iterations is required is the number of iterations the loop iterates, and after those number of iterations the whole data will be available, right. So, this is the pipeline implementation of the loop. Okay. The next is unrolling. So, what is that? So, I am going to unroll this. So, I am instead of writing a loop is effectively basically there are 10 operations, right. So, that 10 operation like C1 equal to A1 plus B1, C2 equal to A2 plus B2, so on, then C10 equal to A10 plus B10, right. So, there is effectively there is no loop here, right. So, I have only 10 operations. So, that is what the unrolling means, that you unroll the loop, you eliminate the loop, right. So, I have only 10 operations. So, I am going to infer 10 adder, this all adder. So, 1 to 10, and since and this is my register storing A, this is the register storing B, and this is the register storing C, and then this is A0 A, this is A1, this is A1, this is B1 and so on, you can understand, I guess. So, this is B10, this is A10, right. So, I am actually multiplying, I am reading array from 1 to 10, array B from 1 to 10, I am just summing A1, B1 and storing it to C1, this is C2 and this is C10, right. So, this is how this whole operation works. So, all this 10 operations is running in parallel and I need only one clock cycle to execute the whole thing, right. And there are two things to be note here. The first thing is that this is not a memory no more, because when you are going to map it something in memory I do not have access to 10 access at the same time. So, in memory you can have maximum 1 or 2 access, because the memory has a port and you have to access the memory through that port, read port and write port. So, whenever you have more accesses, you cannot map this register to this array to memory, it will map it to register and you are reading all these 10 data parallel. You need 10 instance of the loop body. Yes, these are all adder and you are doing everything in parallel, right. So, this is what is loop unrolling. Okay. So, this is something you understand, you need it very fast, latency is only 1 clock, but it need hardware is small number of iteration of the loop, right. And this is the trade off between these two is the partially unroll. So, partially unroll means what? I am not going to unroll the loop all 10 times, instead I just partially unroll. For example, I have given this for the same example, I just unroll by 2. So, the effective code will become this. So, now I am going to, this is 1 to 10. So, this is C 1 equal to A 1 plus B 1 and this C I plus 1 equal to A I plus B I. So, I unroll 2 times and my instead of I plus plus and my loop will be incremented by I plus 2, right. So, that means the loop originally was iterating 10 times, here the loop will be iterating 5 times and in each iteration I am doing the iteration of 2 of the original code, right. So, initially the loop is iterating 10 times, now I am iterating 5 times and in each iteration I am doing 2 set of operations, right, iteration of operations of the 2 iterations in the same loop, same iteration here, right. So, here whatever the data path will be generated, I will have generate 2 again this is kind of a pipeline now. So, you after partially enroll you are going to pipeline it, right. So, I have 2 because I now in the iteration I have 2 operations. So, I am going to insert 2 adder and from the register, this is my memory A and this is memory B. I am going to read 2 data, right, I and I plus 1, this is I and this is I plus 1. So, I am going to read A I and I plus 1 from B, B I and B I plus 1 and then here I am going to do A I plus B I, here A I plus 1 into B I plus 1. So, C I will be generated here C I plus 1 and I am going to write 2 data into the memory C, right, and the write address is also I, this is I and this is I plus 1. There are 2 address and this I less than equal to 10 is the enable, write enable signal for the both the port and this now I is incremented by I plus 2 and that is also writing back, right. So, this is also writing back to this to the actual data path, right. So, this is how so this is the write enable. So, this is how we are going to generate. So, this is kind of a trade off between fully unrolled versus fully pipeline, because now I need 5 cycle to complete, because the loop is iterating for 5 cycle. I am doing operation of 2 iteration at the same time. So, this is kind of a trade off between the actual unrolling versus fully unrolling versus pipeline, and which is your good choice. It depends on your requirement. If your design is very want to execute very fast, then you probably unroll is better, because if you do not your resource does not matter. But if you are bother about the resource, you are going to use as less resource as possible, then you should properly totally pipeline, so that you can generate the minimum number of resource. And if you want to make a middle of this, when probably the 10 cycle is too much and generating 10 adder is too much, then you probably go by an intermediate trade off by partially unroll and then pipeline, right. So, this is the design choice based on your requirement, you have to decide, but you have to understand that all the synthesis tool has this kind of facility. So, you have to choose the right option for your design based on your requirement. Okay. So, this is what we have discussed for single iteration loop, right. So, now if you just go for the nested loop, what kind of design choice you should make, right, because this is the common kind of the coding style. We have nested loops. So, here I took an example of 2 nested, right, for I and for j. So, loop I and loop j, right. So, if you have nested loop, whether how do you choose pipeline, how do you choose unroll, which loop has to be unrolled, which is the better choice, which loop has to be unrolled, which has to loop is to be pipeline, or should we do both unroll, should we do both pipeline. So, these things the choice will come, right, because they are nested loop, and even nested can be more. I just took 2 example, nested depth of 2. So, I am going to discuss now, if you have a nested loop, how to pipeline and what are the choice you should make for your design. Okay. So, I took this example of nested loop 2, and as I mentioned you have different choice now. So, the first choice you can make that innermost loop, that loop j is pipeline. So, you have to pipeline this loop, and if you try to do this, automatically the outer loop will also have to pipeline, because what I am doing, I am just creating one instance of this. So, I need one multiplier and one adder to do this operation. So, I am going to do this, and this is same as this implementation, this pipeline implementation. I have only one copy. This is that pipeline implementation that I have only one copy. So, this way this the inside loop will be this inside loop is a pipeline. So, I have created one instance of this particular loop body, and then since this is going to take 20 cycle to compute. So, this will also automatically it will take 20 more, 20 into 20, right. So, 20 into 20 cycles, right. So, the point is here that if you pipeline the innermost loop, the outer loops automatically get pipelined, and I need only one instance of the resources. So, I need only one multiplier, one adder for this design, but I need 20 into 20, because this loop iterates 20 times, this loop iterates 20 times. So, I need 20 into 20 number of cycles, right. So, but this is something, if you choose the case 1, that you try to pipeline the innermost one, okay, the loop j. The second option is here is you try to pipeline the outermost loop, the loop I, right. So, for my example, the outermost loop is loop I and innermost loop is the loop j. So, if you try to pipeline the outer loop, what will happen? Automatically the outer loop will get unrolled, right. So, you are going to create, since this loop has 10 iterations, it is getting unrolled. So, you are going to create 20 instance of the loop, right. So, that way I explained for the other cases. So, what will happen here? We have to generate 20 instance of the body. So, that means I need 20 multiplier and 20 adder, right. So, I need 20 multiplier and 20 adder. If you try to pipeline the outer loop, and automatically the inner loop is unrolled, and I need 20 cycle, right. I need 20 cycle because the outer loop only get pipelined. So, this is iterating for 20 times and this is unrolled. So, this will take one cycle, all the operations will be executed here, and this will take 20 cycles. So, I need 20 cycle, but I need 20 multiplier and 20 adder. And the third option is that you unroll both, right. So, where then basically in one iteration you are computing all these operations, right. So, I need then for this 20 into 20, that means 400 multiplier and 400 adder, and I need only one cycle, right. But this is not feasible, right. So, the design with 400 multiplier is quite unlikely, right. So, this is not at all a choice. So, to summarize that when you are nested loop pipelining, you can understand that it is better to smart choice is that you try to pipeline the innermost one as possible. So, if you have a say nested depth of 4, you may be decided that the innermost one you unroll, but you try to pipeline the at least second level, not the third level or fourth level, based on your requirement. But it is better to pipeline the innermost one as much as possible, then you will generate the smallest hardware with acceptable throughput, right. So, this is something you have to choose. So, if you have a loop depth of say 4, it is better to say this is say for I, then for j, then for k, and then for L. If not possible, so if you just pipeline this one, all 4 will be pipelined, right. So, you need, so if this it is say L1 time, this is L2 times, this is L3 times, and this is L4 times, your number of time step will be required L1 into L2 into L3 into L4, right, L4. But if you pipeline this one and this is you unroll, then you need basically L1 into L2 into L3 times, right, because this is pipeline, this is unrolled. So, but it will generate 24 times of hardware for this. So, now it depends. So, the idea is that you should not pipeline that outermost one as innermost. So, based on your requirement, you should always try to pipeline the innermost one, right. If your case, if your this number of clock cycle is not acceptable, you probably go for pipelining this. But if you are going to pipeline this one, all these 3 will be unroll all these 3, and it will create a huge hardware, right. So, since the nested loop, you should always think of pipelining the inner level iterations as much as possible. Okay. So, this is what we have discussed about this loop and how to choose to synthesize the loop, whether you should pipeline, whether you should unroll or whether you should partially unroll. Right. So, this is what we have discussed about loop. Now, I am going to move to the another topic which is called loop parallelism. So, there is another topic. So far we have talked about a single loop, right. Now, if you have some multiple loops and in a see what happens. For example, in this behavior say there are two loops, right. This is loop 1, this is loop 2, right. So, if you just write this kind of code, what will happen? This will be iterated first and then this will be iterated, right. So, this is how the sequential code works. But in hardware and then the number of times. So, if you just write this or the kind of RTL that will be generated, that will also follow this one, and what will happen here, the number of time step is required. Since this loop iterates for limit 1 times, this is limit 2 times. So, the number of latency required limit 1 plus limit 2. So, this number of clock cycle is required. Okay. But in hardware you should always think about your hardware runs in parallel. The basic mistake that we always make is that we always do not differentiate how the C works versus how the hardware works. So, in C everything is sequential. If you write say 20 lines of code, the line 1 will be executed, then line 2, line 3 and so on. But in hardware if you have say 10 modules, all 10s run in parallel. So, it may be that module 1 is doing line 1, module 2 is line you can do like this way ki I execute module 1 for line 1, module 2 for line 2 and so on. But in hardware all 10 are available, all the clock. So, when you are writing your C code, you should always try to write such a way that you try to make parallelize as much as possible. You try to utilize the parallelism inside the hardware as much as possible. So, that is something is the point for this loop parallelism. Okay. So, what I am trying to talk about is that there are two loops. If you just write this way, the generated code hardware will take limit 1 plus limit 2 times, because this will be executed first and then this will be executed, right. Now, what is the alternative? The alternative is here is that we try to parallelize this loop as much as possible. Okay. So, the first possibility is that if this limit are same, right. The possibility one is if your limits are same, you can probably merge these two loops, because in the loop you are doing the same operation, right. You are just doing addition, same operations are doing. So, if you have this scenario, you should probably merge these two loops, right, and the kind of code will be generated this, right. So, now I have only one loop and this is limit by limit 1, because limit 1 is equal to limit 2 and all the operations of loop 1 and loop 2 is merged to this, and I just generated one iteration. So, the number of cycle is required here is limit 1 instead of limit 1 plus limit 2, I need now only limit 1 number of time step. So, this is very corner case, because if the two loop body are same, then only you can do that. But if your loop body are not same, so then the next scenario I am going to consider is that your loop body is same, but the limit is different. Okay. So, the case 2 is your limit are not same, okay. You have different limits, but your loop operations are same. Okay. So, then what you should do actually, so you should write a function for this loop instead of writing the whole thing in your main code. You should write a function that is generic way to do that operation, right. So, for example, here since the loop operations are mostly same, here I am just doing x out equal to x out plus ai, here y out equal to y out plus bi. So, this operation is same, only the variable name has changed, right. Similarly, here y out to y1 and x out to x1, only the variable name same, but the type of operation is exactly the same. So, what I am going to do, I can write a simpler function, right, which will do this body, and that parameter to that particular function will be this a, and this output will be y. Right. So, return type will be x or y and input will be a. So, if you just write this, so this is what I have written here is that I write a function where my input is say input I and I have output is o and I have a limit, and the loop I am just doing the same operation, the operation type is same d out plus. So, actually it was written x, see here x out plus. So, what I am doing here, so x d out equal to, so actually it was written like this, right, x out plus x I. So, I just replace this iteration by this, right, because I now make it parameterized. So, I have the input is I have input is limit and output is this, right. So, here I can see that I am always using the data types d in t, data types input types. So, it is not integer. So, it can be 10 bits, 5 bits, 2 bits based on your requirement, and that this is the same loop. I am just calculating the same thing, but in parameter is void, right, and my output will be, it is not void, should be return type should be this O. Okay. Or you can actually pass it by argument. So, both are possible. These are the language specific. So, I am doing this, and now I have just two call here. You can see I just call loop 1 with a x and limit 1, then I call this loop 1 again with b y and limit 2. So, if we just do this, so in the first call it will do the operations of this loop 1, it will do the operations of this loop 1, and in the second call I am going to I call the same function again with this different parameter, and it is effectively going to do the operations of the second loop, right. So, this is something is going to happen, but the advantage of this is big. So, now I have declared these two. So, I have only this one declare this as a function. So, it will create a one function body, right, that or the one module for this, and now you can actually it will so there are two options. If you try to run them in parallel, then it will create two instances, right. You can, it will create, because these two are independent thing, these two loop body are independent. So, you can create two module, and one module will call for this and one module call this, right. So, it depends on your choice. So, you can create two instance or two loop body, or you can actually create one loop body only, and then you use the same loop body or the module just to do this one, and then you can reuse the same body to do the same operation. So, both are possible. So, based on your requirement, you can, if you need only you want to minimize your resource, you can probably make them sequential, so that only one module will be created and that will be reused for both the calls. Okay. This is case 2, where your limit is different, but the loop body is performing similar kind of operations. But if your loop body is also different, then you cannot reuse, always it will create multiple body, but it is better to call them, write them in a function, so that you can, and you can call them whenever it is required, like this, right. So, this is something at least if their loop body are different, you are creating two different instances of the loop body, but still you are actually make it parallel, right. So, what I am trying to make is this is like, suppose you have a loop 1, so where you are doing say I equal to 1 to 100, you are doing say a I equal to b I minus c I, right, and this is loop 1. Okay. And this is in loop 2, if you are doing same thing, I equal to say 1 to 10, but you are doing say x equal to y I into z I. So, I am doing a different operation now. Okay. So, I am doing y I into z I. So, this is your main. So, if you have this, your loop body iteration level, these limits are different, this is 10 and this is 100, and also the operation is different. So, you cannot create a single module to do this, but still what we can do, we can create a module 1 for this, right. You can write a function 1 for this, this is function module 2 for this function, the way I just write this kind of loop, and you can call these two function module 1 and module 2 for main, right. So, you can just do this from main, you can just call module 1 with a, b and c, and module 2 with x, y and z, right. Now, since these two are not dependent, they are dependent, they will run in parallel. So, that is the advantage. So, you always try to merge. So, parallelize the loop, that is because loop will take a lot of time. So, summary is this, you try to parallelize this loop as much as possible, you try to merge two loop if possible, or you can actually if their limits are same and the operations are same, or if it is not, limit is different, then you can probably create a same function body and you call it 2 times, so that either it can be used or maybe parallel body will be created, or if the limits are also different and the function body is different, still you write a module, so that this two module can run in parallel in hardware. And so, this is something we should always think about when you have multiple loops in your behavior. Okay. So, this is on loops. Now, I am going to talk about array. Okay. So, this array is another important aspect in program. So, we use lot of arrays, and this is the most critical thing which actually make bottleneck to your performance of your hardware. Okay. So, usually this array is getting implemented as memory, that means RAM or ROM. Okay. And the problem is here is that this RAM or ROM in the hardware, they are going to access through port. Okay. So, that means, and this hardware typically for synthesis we have only single port or dual port, that means you can maximum read one element or maximum 2 element, depends on your RAM choice. But in C we do not care, we can read say 10 elements at a time from array, but if you have a say multiple access to array element, then it is a problem to for a memory out of it, right. So, either it will if because of there are multiple access to that array, this will be mapped to a big registers, or we need multiple cycle to read the data, right. So, what I am trying to say is that there are say 4 read from array, and this 4 read cannot be done. So, in C you can do it, there is no problem, you just read 4 elements, but in hardware, since you have maximum, say I assume that you map it this into a dual port RAM. So, you can maximum read 2 elements, so you need 2 cycle to read 4 elements, or if your performance is critical, you want to access all the elements at the same time, then you cannot map that particular array to that memory RAM. You have to map that particular array to registers. In register you can have parallel access, but the problem is that if for a big array, it is not good choice to map them to register, because that is your all the register will be utilized, and then it will create a problem, and you for other purpose you need register, you may not use it, right. So, your all register will be used. So, that is something we should always think about, right. There is an example here. So, as I mentioned, there is a loop here where I am just adding 4, I am reading 4 array element and just sum them, right. So, you can see there are 4 access, and if you try to map this array A to some RAM, and suppose that particular RAM is a dual port RAM, then you need 2 cycle to read this 4 data, right. So, every time you have to for every iteration you have to wait for 2 cycle to read all the data, then you do the summation, and this loop iterates for 20 minus 3 means 17 times. So, 17 into 2, 34 cycle will be required, right. But because if you map this array A to this some RAM, okay. But you can see here that this particular array indexes are reused, right. If you just see here, you can see that so in that code for the initial array, so this is A3, A2, so this is 3, 2, 1, 0 location, right. So, in the first iteration I am reading A3, A2, A1 and A0, right. In the second iteration when I equal to 4, I am reading actually 4, A4, A3, A2 and A1, right. So, 4, 3, 2, 1. You can see these 3 elements are common. I am reading them 2 times unnecessary. For the first operations, iteration 1 I am reading them, again I am reading them for iteration 2. Similarly, for iteration 3 it is 5, 4, 3, 2. Again this 4, 3, 2 is going to reuse every time. So, this is an unnecessary read. So, in C there is no problem, because it is just reading 4 elements from array, what is the big deal, but it is a big deal for hardware. It is creating a bottleneck where you are unnecessarily reading the same element multiple times, which you could have avoided, right. So, now you should write this code this way, so that what I am doing here, initially before the starting of the loop, I just read this 2 initially I just read this A2, A1 and A0. I just read A0, A1 and A2 to 3 temporary variable, temp 0, temp 1 and temp 2, and in the loop what I am doing, I am just reading this temp 3, sorry A3, I am just reading A3, and this is already available, this 2, 1 or 0 available here. So, the sum is I am doing this, where I am using this temp 0, temp 1 and temp 3 is already read, they are stored there. So, sum is required. So, I need only one read from memory of array A, right, and then you have to do this shifting, because initially for the next iteration this temp 0, this is your temp 0, this is temp 1 and this is temp 2. Now, for the next iteration this will become temp 1. So, this is your temp, so sorry temp 0, so this is temp 1, this is temp 2. Now, this become temp 1, this become temp 2, and this become temp3, right. So, you have to just shift the things, so you have to reassign the value. So, this is what I am doing, this temp1 become temp0, temp2 become temp1. So, see temp1 become temp0, sorry, this is I make a mistake here. So, this is temp0, this is temp1, this is temp2, right. So, now temp1 become temp0, temp2 become temp1, and that a temp3 become temp2, right. This is your temp3. So, this rewriting is happening, so that for the next iteration I have the right value in of the temp1, temp2 and temp0. So, this is how if you just rewrite this code, you can actually execute the whole loop with only one read per cycle, per loop, and you can understand this, where actually I just what I did, I just reduce this unnecessary memory access, and if you do this, you can actually do this using pipeline throughput 1. That means, you can actually read, you can map this particular array to a single port RAM, and you can actually execute this loop under 17 times, because every iteration I have only one read. So, I need one cycle. So, instead of 34 cycles here, I can do the loop in now 17 cycle. Right. So, this is the some very simple example that actually tell you the logic behind inferring RAM ROM from array, right. So, the key points here is this. So, the number of array access is a big bottleneck in performance, right. So, if you have multiple access, either you need multiple cycle to read them in your hardware, or you have to map that particular array to register to make all the read parallel. That means, you can read all the elements in one cycle, or so which is not a good design choice, right. So, most of the cases you have an option to rewrite your code, so that you can reduce the multiple array access, and you store the you read the data, you store in once and store in local register and reuse, that is the basic idea. So, instead of accessing multiple times, you access each element one time, you store it locally, and then you reuse whenever is required, whatever I have done here, right. So, I do not read this element, this A3, A2 and A1 multiple times. Instead, what I am doing, I am just try to reuse. I read it here for the iteration 1, I use them in iteration 2, I read this 3 for iteration 1, I am going to use them for iteration 3, and so on. So, this is the core idea behind array access. So, this is a very critical thing. You have to always try to make sure that your array is not over accessed, so that inferring RAM or ROM from array is getting hampered because of your access, multiple access. So, you should always think about writing this kind of code instead of this kind of code. Okay. Okay. So, this is something we have discussed. Okay. There is another option with your array, split and merge. So, if you have a very big array, you can probably split it into multiple one, right. So, suppose you have a very big array, if you try to the problem is that if you have a big array, there is a high chance that there is a multiple access and it is not getting inferred RAM, right. So, it is mapping to register, which is a disaster, right, which is a 50K size of array. So, it is better to split it into small array, so that you can actually distribute your access in local to this. So, all the local access is mapped to this, all the accesses that is mapped, so that can be mapped to this, so that you can partition it properly, and you can infer RAM out of this block and this block. Where if you just try to map the big array, probably this cannot be mapped to a single RAM because of multiple access. So, if you split it according to their access, so that non overlapping access is clubbed in together, so then you can infer probably multiple access. Again, this is very design specific, it is not always possible, but you always try to keep in mind that very big array, there are multiple access, and it might create a problem in accessing RAM ROM. So, you can split that array into multiple small block, where all this where the access to these are non overlapping in the sense they are not accessed in parallel. Okay. So, that you can actually map them into different block. Similarly, the other way, if you have very small array, inferring RAM for them is waste of resource, right, because your array your RAM size is 18K, 20K in hardware, and suppose your array only 1K or 2K. So, that time if you do not violate the performance in the sense that this is accessed very early in the loop and this is accessed very late of the of a main code, then probably their access are non overlapping, right. Probably even if you map them, so since they are scheduled in different time step, their access can be can be done through same port. So, then you can probably it is better idea to merge this small array into a bigger one and use that array in your code. So, that instead of inferring 3 RAMs here you can infer 1 RAM, still you can actually execute all the read and write operations there through the single port or dual port of the big RAM. Again you understand this is also very design specific, it depend on your code, sometimes this is not possible, sometimes this is possible, but always you should always think about this aspect of writing code, that should I merge small array into big one, I am going to use it, or I should be I have to split that big array into small one, so that I can infer. The inferring RAM is easy, right, or feasible. Okay. So, this is the another aspect you should think about. The second thing is that third thing is that array as interface, whenever you write a function and it has array input, this function is create a module, right, and it will assume that there is a since there is a array as input, it is something external memory, and this is your function, and it will create some port here, right, so that memory access happen through this port. Okay. So, this is how this will be mapped. But if you have very large number of access, right. So, I have here 8 accesses, this is nothing but if you take this ij location, I am going to read all this neighbor, this 8 location, this is what I have written here 8 location, and just make average out of it, right. So, I am just doing something, and the problem is here there are 8 access, it will create 8 port, right. The problem again is that this number of port is something you should always keep minimum, because in your hardware the number of port is always fixed and you cannot overuse is a problem, then maybe your code may not be mapped to some specific target. Okay. So, idea is again is that you when you have this kind of function array as the input, you try to reuse the array access. Again the same example is happening here, like my previous example, you can see here for this location I am going to use this all 8 location, right. So, you can see here. So, this is my. So, for the second iteration when you are going to access this iteration, these are common, right, these 5 locations are common, only this 3 is the new one, right. So, this location, this location, this location, this location is already read. So, you should rewrite your code this code such a way that you can actually reuse this 5 location, this 5 data you can reuse when you are going to do the average for this node, right. So, that you do not have to create 8 port, instead of 3 port is sufficient, because every iteration you are going to access 3 new data. So, instead of 8 you can only read 3. So, that is something you should always be careful. So, the summary of this is like when you have array at interface, you should always try to minimize the access, so that it can create less number of port. Okay. Okay. So, I will move to the next topic, the array initialization. So, we always initialize some array in our design, right. So, you just define A8 equal to this, and if you do it inside a function or say in your main, every time you call that function it is get initialized. The problem is there, since suppose this is mapped to a single port RAM, what will happen? You need 8 cycle, because you are writing 8 data to the RAM. So, it will take 8 cycle to read or initialize this array, and it is a bottleneck, right. If you call 100 times this function, it will take 800 times or cycles to only the initialization of that array, because this is something suppose this is mapped to single port RAM. But what you can use, suppose your initialization purpose is only once and you are not going to use that initial data more than after the first call, you can probably use static, right. If you use static, then it will be initialized only once and then you are going to reuse. So, that is the basic idea, that is the same concept of C. So, instead of writing only ints A8 this initialization, you can actually do static. If you do static, then it will be initialized only once in hardware and it will be reused. So, it will reduce the number of size, not each call it will be initialized. So, it will save lot of time. If your design is not going to depend on your initial data, the initial data most of the time what happened, that initial data required for only the first iteration for the first call. After that, whenever you call, the whatever you computed, that is used. So, it is better to use static instead of normal initialization, because that is a simple thing, but that will save lot of latency of your design. Okay. So, this is array initialization, another issue. Okay. So, the last topic is like this read only array. So, if you have some array in your design, you are going to read only read, there is no write on that particular array, then it is better to infer a ROM from that, right. RAM is something where you can read and write. So, that can be used for the array, that is something is going to both read and write. but some array is only going to be read, then it is better to infer RAM, and for that you should use const quantifier. If you use a const quantifier, that is a constant array. So, the hard synthesis tool will understand this is a constant array, this is not going to be updated, it will be initialized only once. So, this will be, it will automatically infer ROM out of it, and it is going to be, so it is not going to map it to RAM. So, this is also is useful features that you should always aware of. Using const quantifier for array, which is only read only, helps to infer ROM out of it. Okay. Okay. So, so summary. So, this is what all I have today is like summary is that you the first thing you should always keep in remember that your C code is sequential, right. Your code is sequential, but hardware is runs in parallel. So, you try to write your code so that you can utilize the features of this parallelism of hardware. So, you can always think of writing C keeping in mind that I am going to have a hardware which is parallel. So, that is a very basic thing we always missed. So, that is a key point that you always keep remember. And the second thing is that your data type should be very efficient in the sense it will be exact. You should not overuse or overuse the actual data types. You should always specify the exact data types, because that will determine the data path width. So, which is will save lot of area. So, that is another point. The third point is that regarding this array, you should always minimize the array access, because that will create problem or bottleneck for implementing this array into memory like RAM and ROM. So, you should always, idea is that you always access carefully, you try to reuse the array access, you should not read the same element multiple times during this, you try to save them locally and then you try to use them, right. And for loop, you try to use pipeline as much as possible, because if you do not pipeline, if you unroll everything, it will create a huge hardware which is not efficient, and this is not sometimes feasible at all, right. So, you should always try to create opportunities so that your loop can be pipelined, because that will give you the minimum number of resource usage and kind of acceptable speed. Okay. So, this is something the key points that you should always be aware of for your writing C code or say a high level code for your target high level synthesis tool. Okay. Thank you.